In this video, we'll start using the generator to investigate the properties of multiple sentences at a time. So we'll start with truth functional equivalence. Two sentences are truth functionally equivalent if and only if they have the same truth value on all truth value assignments. So this is the SL version of logical equivalence, right? You have this sort of vague notion of logical equivalence, and then we make it precise in SL by defining it precisely in terms of truth value assignments. Now, the way that you test for this is you take the two sentences, you put them in the same truth table, and then look to see if there's a line of the truth table where the sentences have different truth values. And if they do, then they're not equivalent. And if they don't, then they are equivalent, right? If on every line of the truth table they have the same truth value, then for every combination of atomic components, they're going to have the same truth value. And so then on all possible truth value assignments, they have the same truth value. So we'll look at these two sentences here, if A then B and not A or B. In earlier videos, I said that these were equivalent, and so now we'll prove it by generating a truth table. So let's go to the generator. It's already set up for working with SL. Enter our sentences. And when you're entering multiple sentences into the generator, what you need to do is you separate them with commas. So enter those, go to generate table, and let's do it as main connective only, just to make it a little easier to see. So here, now you can see, I mean, it's only a 4-line table. It's pretty short, right? But you can clearly see, right, that they have the exact same sequence of values under the main connective, right? So these are equivalent. For every combination of values of atomic components, both of the sentences yield the same value, so they are equivalent. If we go and change one of these sentences, so let's say we turn this one into A or B, generate a table for that. Now, what you're looking at are two sentences that are not equivalent, right? For this combination of values here, where A is true, B is false, they have different values. And down here, where both A and B are false, they also yield different values. So the next property we'll look at is truth functional consistency. This applies to sets of sentences of SL. So a set of sentences is truth functionally consistent if and only if there's a truth value assignment on which every member of the set is true. So the way that you test for this is you take every member of the set, you put them all in the same truth table, and generate the table, and then look to see if there's a line where every member of the set has a T under the main connective. And if there is, then that tells you that there's an arrangement of atomic components where that makes every member of that or every sentence in that set true. So then there's at least one truth value assignment where every member of the set is true. And if there isn't a line where every member of the set has a T, then there isn't a truth value assignment on which every member of the set is true, and the set is truth functionally inconsistent. Now, what you may be wondering, though, is this. If you remember from when we were talking about sets, sets can be infinitely large. So you could very well have an infinitely large set of sentences, right? A set of sentences of SL that had infinitely many sentences in it. And then the problem that you have is this: you can't make an infinitely large truth table. Um, in that case, what we do have is this, the compactness theorem. The compactness theorem says that if you have any inconsistent set of sentences of SL, even an infinitely large one, has a finite subset that is inconsistent. So if an infinitely large set is inconsistent, there is at least a finite subset that could be tested in a truth table where you could verify that that finite subset was inconsistent. You don't, however, have an algorithm for finding this inconsistent subset, right? Picking that inconsistent subset out of this infinitely large set. But I mean, the lack of algorithm there is not something that should be surprising. I mean, if you're talking about like arbitrary, infinitely large sets of sentences of SL, I mean, you might not actually even have an algorithm for generating the entire set, right? Or verifying whether, a sentence of SL was a member of that set. So let's look at the generator and we'll look at how an example of how this works. So here's a set of sentences. This set only has two sentences in it, but remember that, sets can be as large as you want, right? So we'll generate a table for this, and I've set this to only display the main connective, so it's a little bit easier to see the relevant information. So if we go through here, what we find is here's a line where both sentences are true. Here's one. Here's another one. I mean, we don't need all three. We only need one. Um, that, though, establishes that this set is consistent because of the fact that there's at least one line where both of the sentences in the set are true. Now, if we add another line to this, let's add this. This is going to be neither C nor A. And we'll generate a table for this. Now, this is going to be a simpler one to go through because there are only two cases where this is true. So we can just focus on these two. Now, there are no lines at this point where all three of these sentences are true. I mean, this one's only true in two cases, and in both of those cases, these two are false, or this one is false. So, given that there are no lines at this point where all three of the sentences are true, we know that this set containing these three sentences, this one is truth functionally inconsistent. So we've established that the first one is truth functionally consistent, and the second one is truth functionally inconsistent. Set gamma of sentences truth functionally entails a sentence P if and only if there's no truth value assignment on which every member of gamma is true and P is false. So this is this is the version of logical entailment that is tailored for SL. And the way that we write this is using this symbol here. It's referred to as a double turnstile. So this is gamma entails P. If gamma is infinitely large, then one of the corollaries of the compactness theorem is that if gamma true functionally entails P, there is a finite subset of gamma that also true functionally entails P. Validity is then defined in terms of entailment. An argument is truth functionally valid if and only if the set of the premises truth functionally entails the conclusion. One thing that's also linked to this is truth functional truth. So remember way back when we were talking about special cases of validity. And we noted that if a sentence is a logical truth, then if it's the conclusion of an argument, the argument is automatically valid. And corresponding to this, if P is truth functionally true, it is truth functionally entailed by every set of sentences of SL. And that actually includes the empty set, right? The empty set, remember, is the set that has no members in it. So if P is truth functionally true, it is entailed by the empty set. And we can actually then use this as a shortcut way of indicating that a sentence is truth functionally true. So if you just write the empty set entails P, then, well, that will pick out all and only the true functional truths. And then we just drop the empty set from the from the way that we write this. So double turnstile P, that's used to mean the empty set entails P, and then that in turn means that P is truth functionally true. So let's look at some examples of using truth tables to test for entailment. So We'll start with this example. The set that we're going to test is going to be A implies B, B implies C, A. This is going to be the set gamma. And then we're going to test whether it entails the sentence C. So we enter all four sentences into the generator, generate the table. I have it set for main connective only. Now, what we want to do is we want to find a line of the table where all of the members of the set are true. And then we want to see if, well, what we're, all the members of the set are true. And we want to see if there are any such lines um, where the target sentence here is false. If you're looking at a big table, you actually, I mean, to try to make this easier for you, you kind of want to look at the sentences and sort of guess at which of these is going to be easier to find. Is it going to be easier to find a row where all of the sentences are true? Um, that's going to depend on how big your set is. If you're looking at a set where, if your set has, say, like 6 or 7 sentences in it, then going through and trying to find the rows where those are all going to be true is a huge pain. In that case, it's actually probably going to be easier to go through, look for the rows where this is false, and then go back and check and see if all the members of the set are true in those cases. Here, the easiest thing to do is going to be to go through and find where all members of the set are true. That only happens in one case, which is here. And in that one case, C, our target sentence, is also true. And that means that this set does in fact entail that sentence. There's no row of the truth table where all of those members of the set are true and the target sentence is false. If we look at another example, let's try this one. If A, then not B, B implies A implies B. This is going to be our set gamma, and then our sentence will be A and not B. Generate this table. Here, both the members of the set are true at this line, and the target sentence is false. So what that tells us then is that this set does not entail the sentence, right? It's possible for both members of the set to be true and the target sentence to be false. And then, of course, what this also does is this also establishes that if you had an argument where these were the premises and this was the conclusion, that argument would not be truth functionally valid. And then in the previous example, if those were your premises and C was your conclusion, that argument would be truth functionally valid.